Right, folks. Welcome back. Today we have Kinetic Theory of Gases fourth part, and today we will be completing Kinetic Theory of Gases. And what we will talk about today is root mean square velocity, Maxwell distribution of velocity, and calculation of mean free path. Um, I hope that you have seen previous videos about postulates of kinetic theory of gases, derivations, and some numericals which was related to this topic. Now, it is necessary to know those things because all these things are intertwined with each other, and I would love you guys to check those videos out before jumping into this video because it's just going to be related to everything. Today it's not going to be that tough of a video because um, it's basically some numericals and derivations. Sorry, related to root mean square velocity and how Maxwell distribution came together to be what it is today. Without further ado, I will jump into root mean square velocity again. We know in kinetic theory mostly we talk about gases, not solid and liquid. So we're supposed to compute about how velocities work and how root mean square velocity for different gas molecules interact, and how it comes into conception. So let's assume for the fact that these are small molecules and it has velocity v3, say v1 or v2. Then root mean square velocity would be v1 squared plus v2 squared plus v3 squared plus dash 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 vn squared by n and root over of everything. This is root mean square velocity for any gases. Why do we compute root mean square in the first place in kinetic theory of gases? Or there might be an analogy for using root mean square not just in velocity but also in current, is because, well, we can compute root mean square like total average mean velocity of gases using equation something like absolute velocity, which should look like the root v1 plus v2 plus v3 plus dash 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 plus vn by n, and absolute of all the values. However, we don't use absolute velocities in this scenario or in any other scenarios because although it serves the same purpose of that, since velocity are vector quantities, it has both direction and magnitude, right? It has both direction and magnitude, and the main purpose of having root mean squared velocity was to serve root mean squared. The main purpose of having root mean squared velocity is to counter the direction part, because in average, if there are infinite numbers of velocity particles, then what's going to happen in the long run is everything is going to cancel out, and we won't be able to compute anything, because if you have infinite velocity particles traveling in all directions, then the mean velocity should be zero. Absolute velocity solves that problem, but the problem itself with absolute velocity is when you try to find when you try to use algebraic expressions with absolute velocity, then what it ends up being is it will have a pointy graphs compared to root mean squared velocity, which will have more smoother graph, so that it's easier to compute and use algebraic expressions with the root mean squared velocity compared to absolute velocity. I hope that makes sense of why the hell do we have root mean squared velocity uh, so prominent in, like, say, statistics or physics or pretty much every other places wherever you see it. So it was a bit of a detour of having y root mean squared velocity, but that's the general idea of using it. Um, so final formula would be VRMS is V1 squared plus V2 squared plus dash 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 plus Vn squared by n, right? What all the formulas of V root mean squared velocity is root over square root of 3 by root over 3 RT by m, where R is 8.314 joule per mole Kelvin, T is absolute temperature, and if you remember from previous videos, especially from Kinetic Theory of Gases video 1, then absolute temperature is ingrained in Kinetic Theory of Gases, ideal gases postulates. So it should be a giveaway that whenever you're solving a problem, then you have to know that there's a direct proportionality of root mean squared velocity with time, and everything else would be constant. M over here is molar mass of gas. When I say molar mass, please do not confuse this m with any other, like, small m given mass, because molar mass would be something like the actual mass of the gas. For example, if CH4 is the gas molecule that we consider, then its molar mass would be the atomic number of carbon. It's 6, its mass will be 12, and hydrogen is 1 times 4. Since they're 4, the molar mass would be 16 grams. So this is what I'm trying to refer to when I say molar mass, and a problem might have given mass, say 4 grams only of CH4. So these two are two different things, and most of the cases and most of the time where we get confused is because we are trying to use molar mass, or we just don't know the difference of molar mass or given mass while solving numericals. So this is something that needs to be taken into consideration, and it is one of the most used equations when it comes to computing root mean squared velocity. Now, I would like to dive into finding how we compute and where does this root mean squared velocity, where does this equation come from. Let me change color. So from previous videos, if you have been following me, then we know that kinetic energy is 1/2 mass mv1 squared plus m2 v2 squared plus dash dash plus 1 by vn squared, right? Which would become half mv1 squared plus v2 squared plus dash dash plus vn squared. What we're trying to do over here is derive equation VRMS for 3RT by m which would be Vn by n times n. Now I want you guys to focus and see how we are deriving back to the root mean squared velocity, because over here what we're going to use is some concepts from physical chemistry or some concepts from molar equations, which would be half this factor itself becomes VRMS squared times m times n. Now we know that number of moles is given by number of moles of any atomic number of moles of any given gas is computed by using the equation mass molar mass by given mass. I'm sorry. Just let me check that. Oh, sorry for the slight confusion. So here, now we know that since we are trying to compute for kinetic energy of 1 mole of gas in 1 mole, in this overall scenario, URMS would have Na, which is Avogadro's number of atoms or molecules, which means the equation over here, let me revert back to the color, VRMS squared would have m times Na, right? Which again, if we write it properly, kinetic energy of 1 mole of gas would be half m Na times VRMS squared, where n is number of molecules and A is Avogadro's number of molecules. M would be simply mass of molecules, and this equation would be mVRMS squared, where capital M is molar mass of molecule or molar mass of gas. So to bring everything together, what we have done here is we are trying to compute kinetic energy of 1 mole of gas, and over here what we did was, since we were computing the root mean squared velocity of say infinite number of particles, right? So instead of computing for infinite number of particles, what we did in it was, hey, what if we compute for Avogadro's number of molecules or Avogadro's number of particles? And with that thought, if we're computing for Avogadro's number of molecules, then we're basically computing the kinetic energy for 1 mole of gas, right? So what if we set up in this place, let me change color, in this place, what if we set up n such that n is equals to Na? Then what we would practically do is, hey, we're assuming for the fact that what if we consider Avogadro's number of molecules? When we do that, then if we multiply the mass times of a gaseous number of molecules, then using molar equation, what we get is uh, m times Na, which is equals to um, m is equals to m times Na, which would be molar mass of gas, which is in turn kinetic energy for 1 mole of gas. So kinetic energy of 1 mole of gas is 1/2 times molar mass of gas times root mean squared velocity. Similarly, if you remember from derivation of video number 2, then we know that kinetic energy for 1 mole of gas is also 3/2 RT, right? We change colors. Now if we equate equation 1 and 2, then 1/2 mvrms squared would be equals to 3/2 RT, and vrms squared, 2 gets cancelled out, would be RT by m 3 root over. So final V root mean squared velocity would be 3 RT by m whole square root of 3 RT by m, which is root mean squared velocity that we wanted to derive from here, from somewhere here. Again, important thing in this equation is V is directly proportional to square root of t. So whenever we are computing root mean squared velocity, then you can use this at your convenience to deduce equation or to solve problems, which comes from postulates that we discussed earlier in first lecture. Now, I think just deriving problems is not enough, so just deriving these equations are not enough, so I'm just going to do some problems, numerical problems, to make sure that you understand what we are doing. To do so, I'll take this problem where what is the root mean squared velocity of hydrogen gas at room temperature? PERATURE, say at 27 degrees Celsius. I'm using Celsius, not Fahrenheit or Kelvin over here. It's because at the end of the day, it doesn't matter because we have to change everything in SI unit. When I say SI unit, this has to be in meters per second, mass has to be in kilograms, and temperature has to be in Kelvin. So that goes untold, that whenever you're solving a numerical problem, especially in physics, it's better to change everything in SI units, because that's how the numericals are supposedly required to be solved. So again, coming back to the problem, V root mean squared velocity would be 3 RT by m, right? Which should be 3 times 8.314 times T would be 287 plus 273, which is 300 kelvins. Which should be at m again. The molar mass of hydrogen is 2 grams, which would be 2 times 10 to the power minus 3 kilograms. So 2 times 10 to the power minus 3, right? Now, if we compute this problem, then I'm just going to approximate the entire problem so that it's easier for me to compute. So I'll just take it as 8 minus 3, which would be 4. Again, 4 3s are 12, 36 100 by 10 to the power minus 3, which should be 3600 times 10 to the power 3, which is basically 3.6 into 10 to the power 6, which is more or less compared to 1. So what I did in here is basically I have approximated the entire value. Instead of using 8.314, I used 8 and then computed it, and after computing it I just got the approximate value, which is the value is supposedly going to be in between the value of 3.6 10 to the power 6 would be in between 1 or 2 times 10 to the power 3 meters per second, because we know square root of 4 is 2 and square root of 1 is 1, and 3.6 falls in between 1 and 2. So I just assumed, for the fact that x would be, let x be that velocity, and 10 to the power 6 square root is 10 to the power 3, so it has to be in between this value. So you can say that the approximate velocity, root mean squared velocity of hydrogen gas is around, say, 1500 meters per second at room temperature. So it gives you a good idea about what is the root mean squared velocity of, say, hydrogen gas in room temperature, in this room or in anywhere else. Let's do another problem. If the root mean squared for hydrogen is x at a given temperature, then find the root mean squared velocity for oxygen at a same temperature. So the problem simply asks for if root mean squared velocity of hydrogen is x at a given temperature, then find root mean squared velocity for oxygen at the same time. So we are supposed to use the equation in this problem is, which is 3RT by m, right? But 3RT by m. But before solving the problem, I would love to give you an intuition of, for these kinds of problem, how we are supposed to think for this problem is, simply we know that VRMS would be dependent on square root of t. But in this case, if square root of t is constant, given the same temperature, so then it should be quite obvious that root mean squared velocity is going to depend upon 1 by m, right? So even before solving the problem, what you should know is, hey, the gas which is heavier should have lower root mean squared velocity at a given temperature compared to the one which is lighter. So having that sort of intuition beforehand, we can compute, say, v root mean squared velocity of oxygen by root mean squared velocity of hydrogen, which would be 3RT by MO2 by 3RT by MH2, right? So 3RT gets cancelled out, which would be 1 by 32 by 1 by 2 times 10 to the power minus 3, given it's kilograms, to 10 to the power minus 3, right? Which should be, again, 2 into 10 to the power minus 3 by 32 times by 10 to the power minus 3, 16, right? So VO2 by VH2 is equals to root over 1 by 16. Now VO2 is equals to 1 by 4 VH2. So VH2 is 4 times VO2, which makes sense because it simply says that the velocity of hydrogen gas at the same temperature is 4 times the velocity of oxygen at the given temperature. And based on the assumption that based on the intuition that we followed here, which was that since if a gas is heavier, then it has to be lower velocity compared to the other gas which is present in the same container at same temperature. So which has been more or less verified over here. I'd like to give another problem, maybe as an assignment, which is, let me check my notes. Right. At 300 degrees Celsius, Vrms of hydrogen is same as Vrms of oxygen at T in Kelvin. Then find T. Options for this answer would be 2400 Kelvin, B 3600 Kelvin, C 4800 Kelvin, and D 6000 Kelvin. What we are supposed to compute is the temperature T, and we are given the fact that, let me change colors, root mean squared velocity of hydrogen is same as root mean squared velocity of oxygen. So Vrms H2 has to be equal to Vrms O2, right? And if we just solve this problem, MH2, which is equal to root over 3 RT MO2, right? So basically here 3R and over here 3R gets cancelled out, and we are supposed to compute. So yeah, 3R gets cancelled out here, and T for hydrogen and T for oxygen is different. So T for hydrogen would be 300 plus 273 kelvins, and mass of hydrogen is H2. So 2 times 10 to the power minus 3 kilograms, which would be again TO2, what we are supposed to compute, and mass of oxygen would be 32 times 10 to the power minus 3 kilograms. And if we equate these problems, then we can get TO2, which was basically your assignment, but I hope now you know what we're doing, and you can compute temperature of oxygen in kelvins. And you can just subtract 273 kelvins to get the value in degrees Celsius. Now, I would love to discuss some proportionality that is in this problem. We know that Vrms is equal to root over 3 RT by M, and as we have discussed earlier, Vrms is directly proportional to square root of 2, which is postulate in itself, right? Now, how can we derive this equation to get it dependent, or to have some other forms of equation? So by using ideal gas equation, which is PV equals to nRT, and we know that we are computing for n equals to 1 mole of gas. So PV would be RT, and VRMS, VRMS would be 3PV by M, right? Which would be 3P by M by V, right? Which is equals to 3P by rho, where P would be pressure of gas, M by V is equal to rho is equal to density of the gas, right? However, whenever we are using the equation VRMS, which is equal to 3P by rho, and we are given pressure and density, if we're giving these two things, then we can just compute. We can compute VRMS directly, right? However, we can't use the fact that VRMS is directly proportional to square root of P, or VRMS is directly proportional to 1 by square root of P. We can't use this assumption, because whenever we increase pressure, density is itself gonna change and increase as well. So we can't assume for the fact that, hey, if pressure is given, that we can assume for the fact that density would be constant. It's not like that. If we change pressure, then density is dependent on pressure, and when both of those things are dependent on each other, then we have to take into consideration that we are not just using the case where we can just assume for the proportionality symbol. There's another case that you might consider in this problem, which should be, say, for constant temperature, which would be VRMS is equal to 3RT by M, right? Now, if we assume for the fact that temperature, which is absolute temperature, is constant, then VRMS would also be constant. See, the underlying idea about root mean squared velocity in ideal gases is, whenever you see constant temperature, you assume for the fact that root mean squared velocity has to be constant, because it's the underlying postulate of the entire ideal gas law. So it is impossible to have something else in root mean square in ideal gas law. However, that's not applicable when it comes to pressure and density, because those are not what we have defined in the postulate, and those are not what we have defined in ideal gas law equations. So I think the video has already been too long, so I would break this video over here, and I will start talking about Maxwell distribution of velocity and calculation of mean free path in different video. To that point, if you are confused, then please feel free to text or comment it down in comment section. And if you have any suggestions for me, then I would love to have those. And yeah, keep learning physics. Thank you. I'll see you in the next video.